This is the second video for week number 13. So let's look at, let's begin this video by looking at the following example. So this example gives you, this is an example of a function which is continuous at a point but fails to be differentiable there. Okay, so this is an example of a function which is continuous at a point and it fails to be differentiable there. So let f be a function defined as follows. F of x gives you the magnitude of x for all x in R. Then we want to show that this function is continuous at c equal to 0, but is not differentiable there. Okay. For continuity, we first note that if you write down the distance between f of x and f of 0, right, then that will simply be this one. Okay, that will be the magnitude of the magnitude between the absolute value of x, with the magnitude of the difference between the absolute value of x and 0, and that will simply give you the magnitude of x, which can be written as this, the magnitude of x minus 0. Okay, now given epsilon bigger than 0, you simply set delta to be equal to epsilon. Then from this expression here, you see that if the distance between x and 0 is less than delta, okay, which is simply epsilon, then the distance between f of x and f of 0 is less than epsilon. So that tells you that f is continuous at c equal to 0. On the other hand, if you compute this one here, f of x minus f of 0 divided by x minus 0, f of x is just the magnitude of x, f of 0 will be the magnitude of 0, which is 0, and then you have x minus 0 here, and that will simply give you the magnitude of x divided by x, okay, which will be 1 if x is bigger than 0, and this should be minus 1, okay. So it will be 1 if x is bigger than 0, and minus 1 if x is less than 0. So please note that this is minus 1. Okay, so if you take the limit as x goes to 0 from the right, that limit will be 1. Okay, and if you take the limit as x goes to 0 from the left, okay, of this expression here, that limit will be minus 1. So the limit from the left of this expression is different from the limit from the right of that expression, right? So that means the limit as x goes to 0 from the right of that expression is equal to 1, whereas the limit as x goes to 0 from the left of this expression is equal to minus 1. And since the limit from the left of 0 is not equal to the limit from the right of 0, then the limit as x goes to 0 of this expression does not exist, and that tells you that the function is not differentiable at 0. So this function is continuous at x equal to 0, but is not differentiable at x equal to 0. So we have the following theorem. Let I be a subset of R, and let C be in I, and let F and G be functions on I, defined on I, which are differentiable at C. Okay, so both F and G are differentiable at C. Then, if alpha is a real number, then alpha F is differentiable at C, and the derivative of alpha F at C is alpha times the derivative of F at C. The sum F plus G is differentiable at C, and the derivative of the sum at C is the sum of the derivatives at C. The product of F and G is differentiable at C, and the derivative of the product is given like this one here. Okay, and if G is not equal to 0, then the quotient F divided by G is differentiable at C, and the derivative of the quotient at C is given by this one here. Now we'll do a proof of part A and B, and then we'll leave the proof of part C and D as an exercise for you. So for the first part, we note that by definition, okay, alpha F, okay, the function alpha F if you apply this to x, okay, by definition, right, this is the same as alpha times f of x. That's how we define the function alpha times f. Okay, so if you apply the function alpha times f to x, by definition what you get is alpha times f of x. Okay, so let's take the derivative of alpha f at a point C. By definition, that will be the limit as x goes to C of alpha fx minus alpha fc divided by x minus c, and that's the same as the limit as x goes to c from this definition here of alpha f of x minus alpha f of c divided by x minus c. Alpha is common here and there, so this can be written as alpha times the limit as x goes to c of alpha x minus of f of x minus f of c divided by x minus c, and this is simply the definition. This one here, okay, is simply the definition of the limit of f at c. All right, so this will be alpha times this one here, this one, okay, is simply the derivative of f at c, and so the whole of this expression will be alpha times the derivative of f at c. For the sum, the derivative of f plus g at c, by definition this will be the limit as x goes to c, f plus g at x minus f plus g at c. Now, how do we define f plus g? F plus g, okay, f plus g at x is simply f of x plus g of x. If you apply f plus g to a point x, that will simply give you f of x plus g of x. That's how we define f plus g at the point x, g of x. Okay, that's the definition of the sum of the two functions f and g. Now, so this is just a definition of the derivative. This is just a definition here of the derivative of f plus g at c. It will be the limit as x goes to c of f plus g of x minus f plus g of c divided by x minus c. Now, by this definition here, this will be, this one is f of x plus g of x. It will be f of x here plus g of x. And then this one will be minus f of c minus g of c. Minus f of c minus g of c. This should be g. Minus g of c. That's how we get this one here. Okay? Just simplifying that one above. Alright. So please change this one to g of c. Now, I've already combined them. So then we separate this as, we separate it into this part, okay, and this part, alright. Then we take the limit as x goes to c. You take the limit as x goes to c. You take the limit as x goes to c. And by definition, the first one is the derivative of f at c, and the second one is the derivative of g at c. So you get that this is equal to the derivative of f at c plus the derivative of g at c. So as an example, we have the function f of x given by f of x is root x, okay? So this example says that use a definition of the derivative of a function at a point to find the derivative of f given by f of x is root x for x bigger than 0. Now, by definition, right, f prime x, now f prime at c is the limit as h goes to 0. So this one is more convenient using h instead of x minus c is more convenient in this case. so we are going to use h. So the derivative of f at c is simply the limit as h goes to 0, okay, f of c plus h minus f of c divided by h, okay. So then we introduce this one here at the top and the bottom, okay, root c plus h plus root c, and then we bring it here also, root c plus h plus root c, okay. Then the top, if you multiply out the top, or if you look at it as a difference of two squares, okay, then the top will simply be c plus h minus c plus h minus c, which will give you h. So if you multiply out this, okay, or you simply look at it as a difference of two squares, then you get that the top is simplifies to h, which is here, okay, which is here, right? And the bottom is just as it is. We left the bottom as it is, which is simply this one here, okay? All right. So what you do here, you ignore this. You ignore this one here, all right? Ignore that. It's not supposed to be there. So you see then this h cancels out with that h, all right? That h cancels out with this h. So what you are left with at the top is 1, and at the bottom you have root c plus h plus root c. Now if you take the limit as h goes to 0, right? Let me use this one here. Let me use this one here. Now this will be at the limit as h goes to 0. The limit as h goes to 0. At the top here, you have 1. That h is not there because this h cancels out with that h. So you have 1 over that, which is this, okay? So then you let h go to 0 of this expression here, okay? You let h go to 0, so this will go to 0, right? So the whole of this one will go to root c, okay? This does not depend on h, so it will remain root c. So you end up with 1 over root c plus root c, which is 1 over 2 times root c. So for n x bigger than 0, the derivative of f at x will be 1 over 2 times root x.